Hello. Okay, I'm back. All right, so our lesson for today will just be hopefully relatively, relatively simple. We're just going to do talk about one of the applications of integration. One of the things that integration is used for, and that is, oddly enough, calculating averages, means, to use the correct math word. Now we know how to find the average of something, the mean of something. We know that it's this formula here, put formula, we add up all the numbers, right? And we divide by the number of numbers. So if we add up 10 numbers, we divide by 10. If we add up 100 numbers, we divide it by 100, right? And now that formula works great for discrete values. That is where we've got a list of numbers and we just want the mean of them. But what if we want to find, and very often in the actual practice of science and engineering and business, we want to find the average of a value that's continuously varying. Where there's not discrete values, okay, where you're not finding a list. So in other words, for instance, what if we want to find the average, if we've got, the average daily temperature over a 24-hour period. Now, of course, the temperature is continuously, it's, at its lowest point at dawn when the sun's coming up, or actually just before dawn as the sun's coming up. It rises continuously during the day, not by discrete values, but continuously during the day. And then at some point it reaches a maximum and then starts to come back down again. Well, how do we find what the average value of that is, what the average daily temperature would be? Okay? Well, so that turns out to be a calculus problem. All right? And what we're going to get at here is a little handy-dandy formula that involves taking an integral. And this is the part, by the way, that we're going to need our calculator for, okay, to actually do the integral. All right, so, but here's how the formula works. Okay, so we're going to start with, the one that we know, okay? So here's the formula that so if we wanted to say here, if we wanted to do the average, get the average daily temperature for this 24-hour period, from dawn on one day to here's noon, and then 24 hours would be dawn the next day. So one 24-hour cycle. So it goes up and it comes back down again. So one way we could do that, obviously, would be to go outside and take a temperature, once every hour, say. So an initial temperature at time 0, and then every hour, right, up to hour 24, which would be the last hour, we would take that, right, and we would measure those, and you could see that it would add up to 24. Now the way I've written, and then we would divide by 24 the number of hourly measurements, that we're adding up, right? Okay, so notice I've written it as f of t, because f is actually the temperature function. F of t is this curve which measures over a 24-hour period what the temperature is. And so the temperature at any given time, you understand, is going to be the value of f of t, the height of that curve, right, at that point. So, f of 12, for example, would be right up there. That would be f of 12. And maybe f of 13 would be that temperature right there, a little bit lower. F of 0 would be, f of 0 would be right there. Does that make sense? So this is f of t1 is the temperature at time 1. F of t2 is the temperature at time 2. Little t is the time, it's not the temperature. So f is going to f of t represents the temperature value, okay? Now, that would give us a value, right, obviously, but we think, well, what if we want to be even more precise? We could say, let's take our temperature every half hour, right? Okay, so we're going to take the temperature every half hour. Well, that would involve, over that 24-hour period, taking the temperature actually 48 times, because you can see that would be a half hour over over a half-hour interval, we would divide 24 by the width of each interval, because we want to take it every half hour. That would be, which is delta t, you understand, O, which would be 48. So far, so good? So we'd have 48 intervals here, and then we would take the height, take the temperature at each of those 48 times, and up at the top here, we'd have 48 intervals, 48 temperatures to add up. That make sense? Okay, so maybe this is starting to look like a Riemann sum, because it would be the width of the interval, right, and the height, which is what we did to do a Riemann sum. And then more formally, we could do, if we wanted a more precise measurement, we could take it every 15 minutes, which would be every quarter hour. So we could divide by 1/4 here to find out the number of intervals, right? Or every minute. So we would divide by the number of minutes in 24-hour period, where the intervals are getting shorter and shorter and shorter, or rather, the delta t, in other words, is getting smaller and smaller and smaller, and in number of intervals, time intervals, is getting larger, and if n is the number of time intervals, that's getting larger and larger and larger, and this may start to sound like what we did to calculate a Riemann sum, right? So we end up with this down here, all right, where we're going to take here, actually right here, we're adding up all of our temperatures, right? And then we're going to divide by whatever 24 divided by delta t was, right? Because in the case of every hour, we just divided by 1. In the case of every half hour, we divided by 1/2 and got 48 intervals. If we did it every 15 minutes, that would be 1/4 of an hour, right? And so we would divide by 1/4, right? And so to get the number of numbers that we have to divide by, it would be 24 divided by whatever delta t is, whatever that time interval is. Every half hour, every quarter hour, every 10 minutes, which would be every 1/6 of an hour, right? And then in that case, we would be dividing by 1/6. Okay? Now, at that point, so that hopefully that makes sense. Now we're leading up to a handy-dandy formula here is where we're going. So hopefully now we're going to do a little bit of arithmetic here. Notice that what we can do with this guy, we can simplify that. We can multiply, remember, delta t by this, by the reciprocal, which is delta t over 24, right? And then delta t over 24 on the top, right? And that entire denominator cancels out, and we end up with this run here times delta t divided by 24. So we end up with f of t1 delta t1, f of t2 delta t2, all the way up to f of t to the t sub n tn divided by 24. Now hopefully you recognize that as just a Riemann sum. We're multiplying the height of the rectangle times the width of the rectangle, the height of the rectangle times the width of the rectangle. So we're adding up a bunch of rectangles, right? The areas of rectangles, but then dividing by 24 to get the average, right? And that gives us, and I want you to look at this. I'm going to zoom in a little bit on that. Excuse me while I zoom in. We take this 24 was on the inside, and we can factor it to the outside and get 1 over 24 over on the outside, f of, from 1 up to n, f of t, delta t. That was our Riemann sum formula, right? And remember what we did with that. Zoom back out again. We imagined that we let the time interval n, or delta t, gets smaller and smaller and smaller. 15 minutes, 10 minutes, 5 minutes, 1 minute, a half of a minute, 30 seconds. Each one of those written as a fraction of an hour, right, would give us more and more time intervals, and we let the number of time intervals, the number of times we're going to measure the temperature over that 24-hour period, go to infinity. Well, that gives us, this gives us the definite integral of 1 over 24 from 0 to 24 f of t dt. So we're going to take the definite integral, which is the area under the temperature curve, and then simply divide it by that time, divide it by 24. Okay? Now that leads us kind of in general to this averaging formula here. Now, if we want to calculate the average temperature over any time period, we did from time 0, the beginning, dawn of the first day, to hour 24, dawn of the second day, we could do the same thing. We could average, what's the average temperature from hour 12 of the day up to hour 24. So we would, in that case, it would be hour 12 up to hour 24, but in this case we'd only divide by 12 because we're only averaging the second 12 hours. That gives us this formula here. If we want to calculate the average temperature over a time period from A to B, it's going to be 1 over B minus A multiplied by the definite integral A to B of f of x dx. Okay, now that says average temperature because f of t was our temperature function, wasn't it? But in fact, f of x can represent any function you want. So this doesn't have to be the average temperature. It can be average of any kind of a function over any x period over any interval on the x-axis here from A up to B, right? And we just have to get the area under that curve and divide it by whatever B minus A is, whatever the interval length is, okay? Now, so here is a picture of how that works, okay? So in effect, what we're doing is we're calculating this definite integral. So here is the temperature function here, you understand, right? From A to B, so from 0 to 24, let's say. So this is what we want the average temperature here. Each one of these represent an average. We want to know where to set this line to make this f of x here be whatever the average temperature is. Well, here's what we just did. What we do is we calculate the area under this curve, which is the area under the f of x, the f average. So this represents f average. So this line right here is f average, whatever that average temperature is. We find the area under that curve, which is A, the area. Now remember, area is length times width, right? Well, okay. We want to know the length. We're given the width, which is B minus A. So in effect, we're going to find the area by calculating this integral, divide it by whatever the length is, which is the time interval. It gives us back the height of it, which is the average temperature that we want. Okay? So that's how that goes. All right? So that's the basic idea, and this is the thing that you want to remember, because it doesn't just have to be temperatures. It can be any function at all, to find an average value for that continuously varying function. Okay, so let's see here. So let's try an example here. And we just want to think right now I want to think about what the units are. Now let me, oopsie, better zoom, move that out a little bit. There we go. Okay. All right, so here's an example. So first, we're just going to think about the units. Okay. So suppose that C of T represents the daily cost of heating a house, right? That's the average cost, that's the cost per day, you understand. Where T is the units of days after, say, I don't know, January 1st, 2000. So keep in mind that daily cost, the units of daily cost are going to be dollars per day, right? Now, what we're interested in is what the average daily cost would be. Now, that might be represented by this. Now, this situation might be represented by this graph down below. So here is day 0, which was January 1st, 2020, right? T is the days after January 1st. C of T is the cost per day, the rate at which we have to pay, dollars per day that we have to pay for our heating. Okay, so what would be? Okay, so what would be the area under the curve? If this is dollars per day and this is day, then the area under the curve would be total accumulated cost of dollars, the total amount that we would be paying. So let's interpret these integrals here. What would this integral here be? From 0 to 90 of C of T dt. Well, 0 to 90 means the first 90 days after January 1st, so about the first 3 months, right? C of T is the cost dt. So in terms of units, C of T was dollars per day. That's that one. T, that's days, right? And we're literally multiplying there. Remember, it's height times it's length times it's height times base, right? We're multiplying those. Can you see that the days cancel out and we get dollars? So that means that when if we just do this integral here, it'll give us the total accumulated cost of our heating for the first 3 months of the year. Got it? Now, what would this integral mean? Well, we're going to take that total dollars, right? And we're going to multiply it by 1 over 90, which, oh, it's no coincidence. That's 0 to 90. That's the interval from A to B. So this is, we're going to take this integral, this total cost integral, and divide it by this interval of, which would work out to be, as you can see, 1 over 90, right? So this is, what that means is it's this integral, which was the total cost, divided by 90 days. So it's the integral units, which we just did, dollars per day, multiplied by dollars, divided by units of days, which is days, right? Those still cancel out. And what we get back again are dollars per day. But this is because we divided by 90, which is the number of days. This is not just any old dollars per day, but the average cost of dollars per day for that first 90 days. Okay, does that make sense? So we just had, what's the total cost, accumulated cost, divided by the number of days, gives us the cost per day, right? It's just that we had to use this integral because the cost of heating a house per day is a continuously varying function. Okay, so now one more example here, and that's all I'm going to need from you guys here, and then you guys will be able to get going on your homework. Now here is, we're going to have an example of actually calculating a cost, all right? And we'll probably do an example 3 too. Let's say we do example 2. Let's say the population of Mexico in millions since 1980 can be modeled by this function here. Don't worry about where that came from, but that's just something you could look up, something you could Google. All right, let's say that that's the correct function. Notice that this is the initial amount, and this is the exponential function that shows the population is growing exponential. And if you think back, this 0.026 indicates that the population is increasing at a rate of about 2.6% per year. Okay, so what we want to know is, if we know that that's its rate of increase, what was Mexico's average population from 2000 to 2020? So that means is, we're going to, in effect, making a little sketch graph here, right here. Can you see that? Yes, you can. Here's the population. That's 1980. That's 2000. That's 2020, right? We want to know, if this is each of these represent what the population level is, we want to know what the average population is, okay? So the average population, what we're going to do is we're going to use our formula here, where it's 1 over b minus a times the integral times the function f of x, the rate of change function, integrated from a to b. Okay, so here's how we write it. So based on the fact that 1980 is year 0, 2000 would be year 20, so we're going to let a be 20, and 2020 is 40 years after that, so we're going to let that be, b will be 40. So we're going to put 40 in for b, 20 in for a, 20 up to 40. We just plunk the function in, right, to t dt. Now how do we, and then so here it is, then 40 minus 20 is 20, so we just evaluate this. Now, how do we do this bit here? This is the bit you're going to do it on the calculator using the procedure that we showed, using the numerical integration function on your calculator. Okay, so if you do that, if you evaluate this function on your calculator, you get this, 2942.66 multiplied, that's the total population increase from 2000 up to 2020, divided by 20 years, that gives us the average population change per year. So the average population for Mexico from 2000 up to 2020 is 147.3 million year, 0.13 million. This is the average population over those 20 years. Okay? Very good. Okay, so that's how that goes. Okay, so let's see. Let's try. I think I can squeeze in one more example here before I have to sign off. So let's say we want the average. We want to average this function here, 3x squared, from on the interval 0 to 3. Well, actually on the interval from 1 to 3. I'm going to do this integral. 1 over 3 minus 1, 3x squared dx from 1 to 3. Okay? So I whip out my calculator, right? And I very quickly, math, I'm going to do it here, math, choice 9, I want from 1 up to 3, and what was it? Oh yeah, 3x squared, 3x squared dx, boom, Mr. Calculator says that's 26. So this is going to be equal to 1 over 3 minus 1 is 2, 1 over 2 times 26, which is 13. That's the average. That's the average function value from 0 up to whatever. That's the average function value of 3x squared from the interval from 1 to 3 is 13. Okay, that's the average f value. That's it. Okay. All right. That's enough to get on with for today's lesson. You're going to go ahead and you're going to, I'm going to have the homework posted in a few minutes. Bye.